Good day. My name is Rhys Gesmundo, and the topic that I will be discussing is about strength of materials, which is all about simple strain. So, what is simple strain or simple stress? We all know that when there is a force acting or is applied in a material, there's a tendency that the material will be deformed or worse, will break, especially when the force exceeds the maximum allowable stress that the material is capable of. So stress is expressed as the ratio of the applied force divided by the resisting area, or in formula, stress is equals to force divided by the area. So this is the applied force in a specific area or body of a material. The units are MPa and PSI. Megapascal, which is for SI unit, and PSI for English unit. It is the expression of force per unit area. The structural members that are subjected to external forces and induced forces. So it is important that we know or we consider in our designs the allowable or the maximum stress that a material is capable of, especially when it will be subjected in a different force loading. So there are types of simple stresses. We have normal stress, shear stress, and bearing stress. Force is applied perpendicular to the cross-sectional area of the material. It can be tensile stress or compressive stress. So we can say that when the force is applied perpendicular to the cross-sectional area of the material, it is a normal stress. For example, this bar. This bar is in tension since it has outward forces on both ends or away from the body of the bar, which tends to elongate the material. While in bar in compression, the forces are inward, or so it means the tendency is that the material will shrink because of compressive force. Second is shear stress. Force is applied to resisting area. And then lastly, bearing stress, contact pressure between two bodies. So I will be giving examples or problems regarding these types of simple stress. So for the first problem, a hollow steel tube with an inside diameter of 100 millimeter must carry a tensile load of 400 kilonewton. Determine the outside diameter of the tube if the stress is limited to 120 meganewton per meter square. So we have a hollow steel or a steel that has a hole in the middle. So we have two diameters, the inner diameter and the outer diameter. So it said that the inside diameter is 100 millimeter and it has a tensile load of 400 kilonewton. Since it is tensile, the direction of force is perpendicular to the cross-sectional area away from the surface. And the allowable stress is limited only to 120 meganewton per meter squared or 120 megapascal. So we are looking for the outside diameter. Our formula is stress equals to force per unit area. So we have a given force of 400 kilonewton and a given stress which is 120 megapascal. So 120 times 10, since it's mega, raised to 6 Newton per meter square is equals to 400 times 10 raised to 3 all over the area. So in terms of diameter, the area of the circle is equal to pi. The area of the circle is equals to pi times diameter squared all over 4 minus the smaller circle, which let's say small d all over 4. So we can factor out the pi over 4 here. We have a given of 100 millimeter diameter. The answer that we will get is 0.11935 m. Or when we convert it in millimeter, it will be 119.35. So for our next problem is consists of shear stress and bearing stress. So the lap joint shown in figure is fastened by four 3/4-inch diameter rivets. Calculate the maximum safe load P that can be applied if the shearing stress in the rivets is limited to 14 kSI and the bearing stress in the plates is limited to 18 kSI. Assume the applied load is uniformly distributed among the four rivets. So we have an applied load which is distributed evenly among the four rivets, which is these four circles. So we have a stress for the shear and a stress for the bearing. What we are looking for is for the maximum load P. So our allowable shear stress is 14 kSI and our bearing stress which is 18 kSI. So for the area of the rivets, we use the formula of the area that we already used in the first problem. So for the area of the rivets is equals to pi times the diameter, which is already given, 3/4 squared all over 4. Where the answer that we will get is 0.442 inch squared. So we have two conditions which are the shear stress and the bearing stress. For the shear, we have shear stress equals to V over A. Since we have four rivets, which has an evenly applied load, it means we have four shears here. So it will be 4V equals P. Therefore, V equals P over 4. So our shear stress is 14 kSI. 14 kSI is equals to P1 over 4 multiplied by the area of the rivets, which is 0.442 each. When we solve this, we will get, therefore our P is 24.752 kips. So from the bearing stress, our stress is equals to PB over AB. We solve for the AB where AB is equals to DT equals to 3/4 times the thickness, which is 7 over 8. The answer that we will get is 0.656 inch squared. So we have also a 4 PB, which is equals to PB over AB. So our bearing stress for here is 18 kSI, which is equals to P2 over 4 multiplied by the AB, which is 0.442. 656. After solving this, we get 47.232 kips. Therefore, our maximum load that can be applied for the plate is P equals to 24.72 kips, which is the smaller for it to be safe.